In this video, we're going to conclude the proof that Rpn is a manifold, so there are two things left to check. Firstly, that it's locally Euclidean of dimension n, and secondly, that it's second countable. So, to see that Rpn is locally Euclidean, first of all, let's just remind ourselves. So Rpn is a quotient of Rn plus 1 without the origin, where points on the same line are said to be in the same equivalence class. And so if we consider, if we let pi from Rn plus 1 without the origin to Rpn be the quotient map, then what we can do is, for each I from 1 up to n plus 1, if we let ui tilde in Rn plus 1 without the origin be the set where xi is not equal to 0. So this is equal to the set of x1 up to xm plus 1 in Rm plus 1 without the origin, where xi is non-zero. And then ui tilde is what's called a saturated open set. So what does this mean? Well, ui tilde in Rm plus 1 without 0 is said to be saturated with respect to the quotient map pi if ui tilde is the entire pre-image of its image. So that means we have that ui tilde is the pre-image of pi of ui tilde. And in general, a set U is called a saturated open set. Needn't be open, but just a saturated set if it satisfies this property that that U is the pre-image of pi of U. So a set is saturated if and only if it's the union of fibers. Okay, so that will be useful because we can conclude if we let ui be the image under this quotient map of ui tilde, then it follows that ui is open. And so you can prove that any surjective continuous map takes saturated open sets to open sets. So ui is open, and moreover we can say that pi restricted to ui tilde, which goes from ui tilde to ui, is a quotient map. So there's a lemma that says if U is a saturated set, then pi restricted to U is a quotient map. And so now if we define a map phi from ui to Rn by phi, and then if we take the equivalence class of x, which in coordinates is x1 up to xm plus 1, and if we define this by x1 over xi, all the way up to xi minus 1 over xi, and then we're going to omit the term with xi and keep going. And then we can see the image of this is in Rn, because it only has n components, and this definition is okay because xi is always non-zero on ui, And we should check this is well defined. That is, we should check that something else in the same equivalence class has the same image, and we can check if we replace x by something else in the same equivalence class, so something of the form lambda x, where lambda is a non-zero constant, then in fact we'll get exactly the same thing, because we'll have lambda x1 up to lambda xn plus 1, and then we can see the lambdas are going to cancel out. So in every term, lambda cancels out, and we really do get the same image. So this is the same as this. So therefore, this shows that phi is well defined. And then, furthermore, because phi, well, in fact, if we call this, I should have said phi I. So phi I is well defined, and because phi I composed with pi is continuous, it follows that phi I is continuous. That's by the characteristic property of quotient maps. And in fact, phi I is a homeomorphism. So why is it a homeomorphism? Well, it's continuous. We can see that from the definition. But because it's each component is a quotient of polynomials, but we can also say that, but we also need to show the inverse is continuous. So what is the inverse? Well, the inverse is given by phi inverse of u1 up to un is u1 up to ui minus 1, and then a 1, and then ui plus 1 up to un. And you can check that that's the inverse, and as we can see from how that's defined, that's also going to be continuous. So that proves that the ui phi I are charts on RPN. So this shows that RPN is locally Euclidean of dimension n. So the only thing left to do now is to explain why RPN is second countable. But each of these UI, we've shown are homeomorphic to an open subset of Rn. In fact, homeomorphic to Rn itself. So each UI is homeomorphic to Rn, and we know Rn is second countable, and therefore each of the UI is second countable. And these charts, the UI cover RPN. RPN is the union from I equals 1 to n plus 1 of UI. So this is a finite union of second countable spaces, so RPN is therefore second countable. And that concludes the proof. So that proves that RPN is an n-manifold. And we're done.